we are going to discuss mathematical part of molecular collisions. In this, the first one is a collision cross section. The collision cross section definition and all already we covered in the previous video. So here this is a collision cross section, and it is mathematically area of this particular circle, and the collision radius, that is sigma. As a result, area of this particular circle will be equal to pi sigma square. Collision cross section is equal to pi sigma square. And the next one is a volume of collision cylinder. So this is the collision cylinder created by this particular gas molecule, and its volume is the product of two terms. One is a collision cross section. So here this is a collision cross section into length of collision cylinder, length of collision cylinder. So here cross sectional area of this into length of this particular cylinder will be equal to volume. So collision cross section just now we derived, that is pi sigma square. Length of collision cylinder in the previous video already we discussed, that is the product of two terms. One is relative velocity of the gas molecule and another term is delta t. So ultimately volume of collision cylinder is equal to pi sigma square root 2 times of u average into delta t. This is a volume of collision cylinder. And the next term is a dependence of n star on pressure and temperature. So first here you have to know what is n star. After that, how it depends on a pressure and temperature. So here let us take a ideal gas equation, that is PV is equal to nRT. In this, n is a number of moles of the gas. This n can be written as number of molecules, number of gas molecules present by Avogadro number. This is number of molecules present, and this is Avogadro number, and that is equal to number of moles. Or send this volume term right side. As a result, from this expression, P is equal to n star, you are sending volume term right side, n star by V, and here this is RT term, we have RT term, and also here we have Na, and this is a molar gas constant divided by Avogadro number, that is a gas constant per molecule, which is also known as Boltzmann constant. So ultimately the pressure of gas is equal to n prime by V into kT. In this, the terms, this is Boltzmann constant, gas constant per molecule, and this is absolute temperature of the gas. This is number of gas molecules present in the given sample, and this is volume of the gas. Now we are going to find the number of molecules per unit volume, number of molecules per unit volume. So here in this, n prime number of molecules are present in V liters, for example. Now if you take a 1 liter, how many molecules will be present? If you calculate, you will be getting number of molecules per unit volume. If you do cross multiplication, you will be getting that n star is equal to n prime by V. So n prime is the total number of gas molecules present in a V volume. If you want to find number of molecules present in unit volume, that will be n prime by V. So n prime by V, that is equal to n star. So from this n prime by V, that is n star, send this kT left side, that becomes a P by kT. In coming derivations, we will be using this expression many times, so that's why n star is proportional to, is directly proportional to P by T. It is directly proportional to P and it is inversely proportional to T. So this is effective number of molecules, otherwise number of molecules present per unit volume. This is the pressure